This week and last week alone, I've gotten over 300 comments of people saying common neutral this, common neutral that, common neutral is a wrong connection, common neutral is a disaster, common neutral will do this, common neutral will blow your entire neighborhood, common neutral will blow your inverter. But one thing all of you have failed to do is to explain to me why a common neutral is a wrong connection. But don't worry, I will break down an inverter for you on this video. So this is a power stage of an inverter, but for you to understand this, we need to go back to the basic block diagram of an inverter system. And if you notice, we have only 4 blocks here, and this is all you need to understand how an inverter system operates. So the first thing we have here is a battery, which is your battery that you have to invert into an AC. So this is what we are trying to do. This battery is 12 volts DC, right? Because it is a direct current. We want to get it to 220 or 230 volts. Let's say just 220 volts what? AC current. Let me put the AC here so you see it. So we want to move from 12 volts to 220 volts, but not just moving from 12 to 220 volts. We are now changing it from DC to AC, which is the function of an inverter system. And in this block diagram, I will now explain it to you. Now, your battery is this way. This is the form for a direct current. You see, it is straight. After the battery, the first stage we have here is called an oscillator. So on this stage, we generate the alternating current, right? So the battery powers the oscillator generates that alternating current into 2 parts, the upper cycle and the lower cycle. So over here, you generate an alternating current, but the signal will be very weak, usually around 5 volts. So this will be 5 volts positive and 5 volts negative on this end. And what is powering this? The battery. Then this will generate this voltage in form of AC. Now this AC is weak enough for what we want to do. You see, what we want to achieve is a 220 volts AC. This battery is a 12 volts battery. The AC signal we've generated already here is just 5 volts. It's not even up to the voltage of the battery. Then we move to the next stage, which is what? The driver stage or the power stage of an inverter system. This is where you get your MOSFET, your IGBT and the likes. So what this does is to make this guy stronger, right? To amplify the signal coming already. We've generated it here. It's just not amplified to be at the level of the battery. Because when we talk about amplification is different from generation. Generation is that you are going from nothing to something. That's you are converting another form of energy into another form of energy, just like you have on your solar panel. But for an amplification, it needs to have a reference. For example, this signal here is 5 volts. So what is happening on this driver stage is to amplify this 5 volts to the voltage of the battery. In this case, the battery is 12 volts. So here we will now have a stronger what? AC signal, which is now 12 volts. So this is 12 volts negative and 12 volts positive. So you see what happened here? We generated the AC signal here, but it is very weak at 5 volts. We then amplified it on the driver stage to what? To the voltage of the battery, which is now what? 12 volts. But this 12 volts AC is still not enough. We are looking for what? 220 volts AC, and that is where the transformer comes in. Transformer transforms AC current from one voltage to another. It could either be from a lower voltage to a higher voltage or a higher voltage to a lower voltage. And in this case, we want to transform this AC voltage from a lower voltage to a higher voltage. So in this transformer stage, this is where to now amplify this AC signal we've already generated to what? To 220 volts that we want. So this will be 220 volts on the negative side and the positive side. So this will be the negative 220 and the positive 220, the AC signal. So you see how we went from the small signal we generated there to the bigger one that we did the amplification here. Then we transformed it to what? To the 220 volts we need as our output. So you see how we moved from this to this, from 12 volts DC to what? To 12 volts AC. So if you notice, the first thing that happened was our 12 volts DC was here. It powered the oscillator. The oscillator generated what? A 5 volts AC, right? Then it amplified it to a 12 volts AC. So you saw the signals are AC, AC. It was now stepping up to we get to our desired 220 volts AC. Now that you've understood the working principle of a basic inverter system, let's get down to the power stage. What actually happens there? Remember, this is the block that does the amplification, our power stage. If you notice, This is a 24 volt system. We can still do 12 volts here, either way. And this is our transformer that transformed our 12 volts AC to what? To 220 volts AC. And this is the power stage we are talking about. You see the positive side and the negative side. This is where the oscillator feeds in the 5 volts generated, the positive side and the negative side. And on this end, the battery positive terminal will be connected to this center part of the transformer. This is the input side of the transformer now in this case. And the negative side is already connected to these two ends and these two ends. So whenever this switches, it takes that negative and puts it here. So you will now have the positive of the battery terminal here and the negative terminal here, which will now energize the transformer. And it will transform that voltage from that 12 volts that we'll have here to 220 volts on the output. And when it does on the negative cycle too, it does the same thing. This center part, we usually call it a center tap. So what now happens, you see that we've generated our 220 volts on the output. We will now have our live and we'll have our neutral. So for all of you talking about common neutral, this is now the inverter output. Now, when we want to charge our inverter, we are now putting power back on the inverter. Because of cost efficiency, this transformer will still be used as the input transformer to charge the batteries, not a different transformer. So your power will still go back into this terminal. What does that show you? That your neutral is also still coming back here. This is where your power leaves. This is where your power comes back in. Your inverter inverts your battery power to AC and it gives it out through these two terminals as live and neutral. When you still want to charge this inverter, it will still go back through here. So even when you switch these two, neutral goes here, live goes here, you see that everything will still work perfectly fine. The only thing is, because there are also some parts we're not discussing which has to do with the switching of the inverter and the lights. The neutral will not be on the live, and most inverter only switches the live line, which will not mean that the live will be on the neutral line that didn't switch while the neutral is not being switched off. But that's not the case we are discussing here. But you'll now understand that even when you switch these two, nothing will still happen. And when the input comes in, it is still that same neutral. So for those of you arguing on my comment section, this is now for you. So this is our inverter now, right? This is inverter. This side is our output and this is our input. We'll have our two terminals here, our two terminals here. This is live, this is neutral, and this is live, right? This is in, this is out, which is this place. So you see this and this is connected here, giving output. When the inverter wants to charge, what still happens? These two parts is to these two parts where your mains, your grid or generator will come in and use this transformer to charge your battery, using this MOSFET to still control the charges that is going to your battery inside the inverter. You see that these two terminals are technically the same thing. The only difference is your inverter now has a switch. So for example, so this doesn't go to this directly. It now has a relay inside. Depending on the size of your inverter, some will have a contactor, some will use a relay. So when the inverter needs to charge, it switches it accordingly the way it needs to work or function. And this neutral usually goes what? Together. For most inverter cases, this is the basic form of an inverter system. Now let me ask you, as this is the input and you have your grid, right? This is your NEPA light and it goes to this part to charge the inverter. You are claiming you don't want to do common neutral, but most of you are still doing common neutral unknowingly. So your grid, live and neutral has entered here. And this is already connected inside, like you can see over here. And this neutral from the NEPA will still go and connect to the neutral on your changeover. Is that not common neutral already? The neutral of the input and the output inverter is already connected. And the neutral of your grid connected to the neutral of the inverter and still went to the changeover. As the neutral of the output and the input of your inverter not connected on that same changeover as well. It is already connected. You are claiming you are not doing common neutral, it is dangerous, but you are still doing it without knowing. So if you have more questions, feel free to leave it on the comment section and we are going to address it. And if you learned something, click the follow button so you won't miss the next video.